All right, welcome to The Explainer. Today, we're diving into a real quantum detective story, one that might just rewrite a fundamental rule of science.
So it all kicks off with this question that's been driving physicists crazy. Why are some insulators, materials that are supposed to block electricity, suddenly acting like metals? This whole thing, it challenges one of the most basic rules of materials science. Let's get into it.
Okay, so to really get what's so weird about this, we got to do a quick refresher. Think about it like this. In metals, electrons are like a free-flowing river, right? They can move all over the place. And that's what lets electricity flow. And when you stick a metal in a magnetic field, that flow creates this unique fingerprint called quantum oscillations. But insulators, they're the total opposite. Their electrons are locked down tight, like water frozen solid. They don't conduct electricity, so they should absolutely never have that metallic fingerprint. Period.
And yet, you guessed it, in these specific materials, things like samarium hexaboride and ytterbium dodecaboride, scientists were floored to find exactly that. Clear, undeniable quantum oscillations. It's like hearing a whale singing in the middle of the Sahara Desert. It makes no sense. It shouldn't be happening.
So what could possibly explain this? Well, the main clue seems to point to this really strange kind of exotic state of matter. It's something that was predicted over half a century ago, but we've only just now been able to create and really control it in the lab. It's called the excitonic insulator.
So what is an excitonic insulator? Imagine an electron zipping along, and it jumps out of its spot. The empty space it leaves behind, we call that a hole. Now normally they just go their separate ways, but in an excitonic insulator, something weird happens. The electron and its hole become stuck together. They form this little neutral pair called an exciton. Think of them like dance partners who are just inseparable. They're locked in an embrace.
And when you get enough of these little dance partners pairing up, they create this collective energy barrier, what physicists call a gap. You can see it right here on this chart. This gap is the key. It basically puts all the charge carriers on lockdown, stopping any electricity from flowing. So, okay, case closed, right? It's definitely an insulator. Well, not so fast.
So if this thing is an insulator, plain and simple, then where in the world are those metallic signals coming from? That's the big question. And right now, the physics community has kind of boiled it down to two leading theories.
Okay, so theory number one is that the material isn't really just a simple, stable insulator. Instead, it's conflicted. It's got a bit of a split personality.
The idea here is that when you hit it with a magnetic field, the material gets pushed into this really delicate balancing act. It starts flickering, like super rapidly, back and forth. It's competing between its normal insulating self and this weird special metallic state called a quantum Hall state. And it's this constant flickering, this back and forth, that could be creating the oscillations we see.
But what if it doesn't have to switch at all? What if there's another explanation? Theory 2, which is brand new, just came out this year, proposes something way stranger. It says the oscillations aren't coming from the material changing its mind. No, they're coming from deep inside the insulating state itself.
Yeah, a recent paper just dropped this bombshell of an idea. They're basically arguing that the very quantum forces that make the electron-hole pairs, the forces that create the insulator in the first place, could, in a crazy paradox, also be amplifying these metallic signals. I mean, look at the quote on the slide. These interactions are supposed to destroy the Fermi surface. That's the defining feature of a metal. And yet, somehow, they make the metallic fingerprint stronger. It's totally counterintuitive, a really mind-bending idea.
And this is where it gets really wild. Take a look at this chart. It really shows you just how big of a deal this new theory is. The graph is plotting how big the oscillations should be. The blue lines, that's the new fluctuation theory, and they are just gigantic. They completely dwarf the predictions from the old theory, which are those little red lines. Heck, they're even bigger than what you'd see in a normal metal, which is the black line. It's a huge difference.
So let's be clear, we're not talking about a small correction here. This new theory is predicting an effect that could be thousands of times larger than what anyone ever thought was possible for an insulator. This isn't just a new idea, it's a potential game changer.
Okay, so this is a super fascinating theory, right? But is it just a theory? Can we actually test it? Well, as it turns out, a team of researchers might have just built the perfect little laboratory to find out. Check this out.
Scientists at Cornell and UT Austin literally built their own custom excitonic insulator from scratch. They did it by stacking these two different materials that are only an atom thick. One layer is for the electrons, the other is for the holes. And the best part is, they can control exactly how they interact with these little electric gates. For a physicist, this is like a dream come true. It's the ultimate playground.
And wouldn't you know it, in their perfect, super clean, custom-built system, they found them. The exact same mysterious quantum oscillations that have been puzzling everyone. So this pretty much confirms it. Excitonic insulators are definitely where this weirdness is coming from.
Okay, so the big question is, which theory does their data actually support? Well, at first glance, their analysis seems to point to theory number 1. It looks like the oscillations are coming from the material flipping back and forth between that insulating state and the special metallic one, the quantum Hall state. So yeah, that fits the whole competing states idea pretty nicely.
But wait a second. This brand new experimental setup? It's the perfect place to go hunting for evidence of that second, way more radical theory. Is it possible that the clues for that huge quantum fluctuation effect are hiding in their data right now, just waiting for someone to find them?
So here's where we are. We've got this powerful new theory that predicts absolutely massive oscillations. And for the very first time, we have an experiment that's clean enough and controllable enough to actually find them. You can feel it, right? The stage is totally set for a huge discovery.
Now, to actually prove this wild new fluctuation theory, scientists need more than just big oscillations. They have to look for very specific fingerprints, which you can see laid out in this table. For instance, the theory says the oscillations should have a different phase. Basically, their peaks and valleys will be shifted over. It also predicts a whole different relationship with the magnetic field and a really unique signature as you get to super low temperatures. These are the smoking guns. This is the evidence they'll be digging through the data to find.
And this all leads to the big, stunning takeaway. For decades, the rule was simple. To get these quantum oscillations, you needed what's called a Fermi surface. That's basically the sea of free electrons that makes a metal a metal. No Fermi surface, no metallic signal. End of story. But what this new work is suggesting is that the rule might be wrong, that maybe pure quantum weirdness, just these interactions and fluctuations, is enough to make an insulator put on a metal costume without actually being a metal at all.
I mean, this just completely shatters our neat little boxes for metal and insulator. It shows us that the quantum world is so much stranger and everything is way more connected than we thought. So if an insulator can learn to sing a metal's song, it just makes you wonder, right? What other impossible things are out there, hiding in plain sight, just waiting for us to look a little closer?